Hello everyone, my name is Mario de Lucio, and today I'll talk about the numerical simulation and poromechanical modeling of subcutaneous injection of monoclonal antibodies. Monoclonal antibodies are laboratory engineered proteins that function as the antibodies naturally created by the immune system to respond to infection. They bind to the molecule or antigen they were generated against and trigger the immune system to attack it. Monoclonal antibody treatment has proven effective for diseases such as cancer, arthritis, or even COVID-19. The monoclonal antibodies market size has been steadily increasing from $150 billion in 2015 to $200 billion in 2021, and it's expected to grow up to $500 billion in 2030. Monoclonal antibodies are large molecule drugs that require parenteral administration. This is intramuscular, intravenous, or subcutaneous injection. Subcutaneous injection is preferred by patients and caregivers because it allows for self-administration through handheld autoinjector devices like the one showed in the animation. Uh, Subcutaneous injection is preferred because it's more effective. It allows self-administration, and also it reduces drug delivery related healthcare costs. However, it also presents a major challenge from a clinical point of view, which is its low bioavailability. The bioavailability of a drug is defined as the fraction of the drug that reaches the systemic circulation. In the case of MAPS, only 60% of the injected drug reaches the systemic circulation. This problem can be bypassed by injecting larger injection volumes. However, the installation of larger injection volumes entails various challenges. From the mechanical point of view, subcutaneous injection involves a high-speed injection of a pressurized fluid into a highly deformable solid. This causes high fluid pressure near the injection point, which can lead to hydraulic fracture in the tissue, high velocities, higher sometimes than 3,000 millimeters per second at the needle tip, and large deformations caused by the compression of the autoinjector base plate that I showed in the animation in the previous slide, which can produce volume changes of up to 150%. From the numerical standpoint, these strong compressions can lead to multiple locking phenomena related to reaching the compaction limit, or to the fact that the tissue exhibits a nearly incompressible constitutive response at the end drain limit. Also, we can face the so-called insub instabilities, which arise when the numerical scheme does not fulfill the insub condition. Therefore, we need a robust computational approach capable of handling all these challenges. We developed an isogeometric analysis model using a monolithic approach with cubic B-splines. The higher order global continuity provided by the cubic B-splines helps reducing the insub instabilities. To further address the instabilities, we also included the fluid pressure Laplacian stabilization technique. Our mathematical framework is based on finite strain poroelasticity. Here you can see the system of PDs that we're solving with our isogeometric analysis model. The objectives of this research are to, one, analyze the impact of tissue anisotropy and tissue layer waviness with realistic geometries obtained from histological images, and study the effect of the compression exerted by different handheld autoinjector devices. As a constitutive theory, we use a fibril reinforced per hyperelastic model. The strain energy function of this model can be split into two parts. The isotropic part, which represents the elastic energy stored in the ground substance or non-collagenous soft matrix, and the anisotropic part, which provides the energy stored in the client fibers. This model assumes that the fibril bundles are arranged in a basket weave pattern, distributed only in the plane of the tissue. Here, we are also taking into account the dispersion of the client fibers. The bottom right figures show what a perfectly aligned and a randomly dispersed collagen matrix looks like. Histological analysis indicates that subcutaneous tissue is a highly heterogeneous material. Here we can see a histological slice of porcine tissue, which is very similar to human tissue. We observe that the interfaces between the different tissue layers that we are highlighting in pink, yellow, and red exhibit complex morphologies. And also we know that the skin microleaf, the interface in pink, plays an important role in conditioning the deformation of the tissue. To account for these geometric features in our computations, we created a model that allows us to generate realistic 2D tissue surfaces using 1D tissue layer boundaries obtained from histology slides, like the one you can see on the slide. The realistic tissue geometries are generated through a statistical analysis of the stained histology slice using a stochastic tissue model that reconstructs the tissue samples in 1D and 2D using Gaussian processes. So first we identify the boundaries using an autonomous segmentation algorithm. Then we input these boundaries into our stochastic model, and then we generate new data with the same statistical properties in 2D. And then this data is extended into 2D to form a surface. After that, we incorporate the surfaces in our 3D model using the existing B-splines of the isogeometric elements. And we can create realistic geometries like the one you can see in the figure on the left, where we can distinguish the main layers that compose the adipose, the subcutaneous tissue, such as dermis, like dermis and epidermis, adipose, and muscle layer. The numerical setup of our simulation, the regular numerical setup of our simulations is as follows. Our computational domain is a cuboid of size 40 by 40 by 40 millimeters. Regarding boundary conditions, we make the top surface impermeable. We impose zero displacements on the bottom plane to mimic the higher stiffness of the underlying muscle layer. And for the outer lateral surfaces, we use drain boundary conditions. And we consider that the domain is stress-free in the initial configuration. The injection in our computational model is characterized by a source term in the mass conservation equation. And the source term is space and time dependent, as you can see in the equations at the bottom left. The injection model that we use accounts for the physical properties that define a subcutaneous injection of maps, such as the injection volume, the injection time, and the needle radius. We perform an uncertainty analysis to estimate the impact of the tissue layer waviness on the overall mechanical response. For this purpose, we generated 10 different wavy geometries, and we ran the simulations considering the simultaneous action of the injection and the base plate compressing the skin surface. And we take the green Lagrange strain tensor as our metric to compare different geometries. So here we are plotting this slice 2 millimeters below the injection point. We are plotting the green Lagrange strain tensor, and we can see, first of all, we can see difference between a wavy geometry at the top and a flat geometry at the bottom. We take the different wavy samples and we compute the mean and the standard deviation, and we compare them to a flat geometry. And we see that we observe differences of 32% 32% in positive strains and 18% in negative strains. And the highest deviations occur around the outer radius of the base plate. So from these results, we conclude that the tissue layer waviness is important to obtain realistic results in terms of overall mechanical response. Now we study the impact of the auto-injector baseplate on the injection dynamics. The figure on the left, the animations on the left show the time evolution of fluid pressure and the time evolution of velocity magnitude, fluid velocity magnitude, with the velocity streamlines in white. Here we are plotting different metrics. So at the top left, we are plotting the time evolution of fluid pressure around the injection site. On the right, we are plotting the time evolution of maximum principal stress in the tissue. And finally, at the bottom, we are plotting the velocity around the injection site. As we can see, as we increase the force, the patient force, the pressure, the maximum principal stress, and the velocity grow around the injection site. So we conclude that increasing user's force increases peak fluid pressure up to 59%, peak fluid velocity up to 19%, and peak maximum principal stress in the tissue up to 12%. And the pressure distribution close to the injection point is dominated only by the injection, regardless of the patient's force. We also studied the formation of the tissue layers. The animation on the right shows the spatial distribution of volumetric strain, and we see that the highest compressive volumetric strain occurred in the adipose layer below the base plate. Here we can also see the displacement field, vertical displacement field. The maximum vertical displacements are located underneath the base plate. And we also see that the highest dilated volumetric strains occur near the injection site and produce a maximum volume increase of 33 to 35%. Finally, we also studied the effect of different pre-injection techniques like the pinch and the stretch technique that are represented here at the top. So these methods are used by the patients to create an injection site and to ensure that the injection is performed in the fatty layer, in the adipose layer, in the layer, in the yellow layer that we can see in the figures. So these animations correspond to a top view of the deformation of the skin while performing the pinch and stretch. And here we can see animations of the velocity field, velocity magnitude field, and the velocity streamlines during the injection process. From these simulations, we conclude that the pinch technique reduces fluid pressure near the injection site and prevents muscle penetration, which is not desirable during a subcutaneous injection, because we always want to inject in the adipose layer, the fat layer. Thank you so much for your attention.